All right. So our goals for today are to go through these several points. We'll start with the homework from the last class, which was to create a network in a different way. And we also talked about degree distribution. So we'll actually start with degree distributions. Then we implement this other network. So we'll have two different network builders to choose from. We will have random networks as that we already have, and we will have another type of random network. And at the very least, it will give us an opportunity to pit these two types of networks against each other and see whether they are different in terms of how disease propagation is happening between them, in them, on them. And then after that, we will try to sketch a disease propagation model. So I haven't actually tried it. I hope I can just do it because it's, yeah, as we go. Yeah, and we will finish with sketching some logic for potential computational experiments. So we'll have a builder, we'll have a model that actually lets the disease propagate, but we have lots of parameters in this model. We have lots of hyperparameters. We have made lots of assumptions. So we need to make a plan of study, sort of, to take a step back, have an eagle's eye view on this entire picture, and understand what we want to achieve with that and what we're trying to do. All right. So first, let's do the assignment from the last class. So here's the code, mostly the code that we worked with. So we import some modules, and then we have this graph class that allows us to add nodes and add edges, and we can get the list of nodes, and we can get the list of edges. You know what? This should be renamed into get nodes or something. Can I rename them get nodes, because otherwise it's not quite clear how we interact with them. Get nodes and get edges. And this is a system thingy in order to str is a system thing that we need to enable print function so that we could print our graph. And we also made a plot function which is based on network X library, and that just plots the graph. Okay, here's a little test, add edge, so I will replace that with get nodes, get edges. Oh, I should also do this, get nodes, get edges. So let's test that all. Does it still work? Yep, it works. This is a truly minimalistic graph with one edge, but good. So it works, it passed the test. And we have this random network creator that also still works. All right. And we calculated the degrees. By the way, yeah, as you can see right now, these pieces of code live in their own notebook cells, and it's not a very healthy way to keep them in the long term, because it's just a piece of code that like lies there in the field. So we want to compartmentalize it. We want to make it either a method of some decent, reasonable class, or at least a function, so that it doesn't get lost. So that's something we will have to work on. But okay, so first, yeah, this is the degree distribution that we had. Let me copy it here. That's the degree distribution that we have for the current for the current model that creates a random network, but the homework was this alternative way of creating a network in which we add nodes one by one, and every time we add a node, we connect it to one of the existing nodes. So the first node will appear, nothing to connect to. The second node will appear, it will connect to the first node. The third node will appear and will randomly connect either to the first or the second node, and so on. And we talked during the Zoom meeting whether we can expect this network to be different, and there are two important points, well, actually three important points. So if we look at this degree distribution, so one thing that we know will happen is that all points will be connected, because for a random network that we had before, for the fully random network, some nodes are just unlucky and nobody ever connects to them. They just sit there alone. So we have these nodes with a degree of 0, which are nodes that were never connected. But once we implement this thing, this other way of creating a network, all nodes will be connected. So one difference in the degree distribution will be that, like, this thing will go down. There will be no unconnected nodes, right? But another thing is that if we use the same number of edges, and we use the same number of edges, the number of edges in this model so far is the same as the number of nodes. So if we have 100 nodes, we have 100 edges. In this new type of a network, we will also have 100 edges because we introduce a new edge for every node that we add. So the total number of edges is the same, and the total number of nodes is the same, which means that the average degree will be the same. And the way we reasoned about that is if we have, like, every edge, whichever nodes it connects, so there may be like other edges for this node, other edges for this node. What's important is that every edge contributes 2 degrees total to the network, because edge, like, is connected to one node and is connected to the other. So if you count all degrees in the system, every edge will contribute to 2 of them, which means that the sum of all degrees of all nodes in the system is just 2 times the number of edges, which means that as long as the number of nodes and the number of edges is the same between 2 networks, the average degree is also the same, right? Which means that the average degree for this thingy, for the distribution, will stay the same whatever it is. Like maybe like around here is the average, and it will stay the same, which means that when 0 nodes disappear, the average degree cannot increase, even though there will be no 0 nodes, which means that some other small number of nodes will have to increase. So if this one goes down, either this one or this one has to go up, or both. Bad arrow. Like that, right? Okay, so that's one thing. But then the other thing is that, as we talked about, that if you think of what will happen when we add nodes one by one, so we add one node, we have the second one, we add it, we have the third one, we add it, we have the fourth one, it's connected to either of them, we have the fifth node, it's connected to either of them. It feels that, like, if we do it a lot, these nodes that appeared earlier will accumulate connections, right? They will be like those, like, founding fathers of the United States who just randomly claimed the land and then they owned it. So these guys, they will be early to the feast and they will get all the connections eventually. They will be like a rich guys club, which is actually a legitimate term in network theory. So they will end up forming some sort of a hub, a center of this network, which means that most probably there will be nodes with lots of connections. So here, for the random network, the degree stopped at 7, but maybe, like, we'll have like really large degrees. It's not like we'll have lots of points here. Okay, like that. It's not like we'll have lots of points here, but there will be some points here. But then the same logic applies that applied before. So if the average doesn't change, but there appear some nodes with really large degrees, like here, then some nodes with like intermediate large degrees have to decrease. So here again is a summary. So this will go down, this will go up, this will go down, this will go up. Okay, that's our prediction just based on the principles of how this thing works. So let's see, let's implement that and let's check whether our predictions are true. Back here. All right, so how does it work? Let's look at this creation. Let's create a random network. So let's actually make it into a function to begin with. Even before we try the new one, let's make the old one into a function, because otherwise it's kind of sad. So define random network. Then we put all of that inside. We have two constants, one constant, but another constant is just made equal to the first constant. We create a graph, we populate the graph, and then at the end we will output the graph. So return G. And so G equals random network. Gplot. Yep, it works. Good. Alrighty. Let's now make a new cell and alternative creator. Define rich network, rich club network. We will also need to know how many. Oh, actually, n nodes. Let's make n nodes no longer constant, even for the first one. N nodes, and let's give it some default value, like 7. It doesn't matter. And then, so n nodes is now a parameter. It's no longer constant. N nodes, n nodes, n nodes, n edges. Okay, let's make it like let's pretend that let's give ourselves flexibility. N edges, and let's make it none by default. Well, what am I doing? Okay, let's park it for now. It's too complicated. Let's just keep the old logic. And edges equals n nodes. In the future, so right now we don't have control over the number of edges, but that's okay. If we need it, we will change it later. So I need to change that. I need to change that. I need to add. How much did we have before? 100? Okay. Yeah, so everything still works. Good. Good. Okay, time to make this one. Define reach club network, also n nodes. Oops. N nodes equals 7. This is a default value. Doesn't matter what it is. I just want it to run. I don't have to specify n edges here because we will add an edge for every node. So it's kind of taken care of. Okay, so we need to create a new graph. How do we do that? G equals graph. G equals graph. Okay, I forgot okay, so we have add node and we have add edge. These are the two what? These are the two interfaces that we have. So all right, this is just, I just copied it just in case. Okay, so let's write a loop. We need a loop that will go through every node, right? From the very first one to the very last one. And every time it will connect to one of the previous loops. Okay, so our loops have values, which in this case will again be numbers, same as we had it before. For I in range n nodes. So I will be a counter that will increase. We will. So there is a slight difference between the very first node, the 0th node, and all the others. For 0th node, we just add a node. For all other nodes, we connect it. So if I is 0, just g add node I 0. Right? Else, for all other nodes, we can do g add edge. I don't even have to add a node, because add edge, the way we wrote it originally, if we add an edge to a node that wasn't defined before, it creates it. It's just how we wrote it, right? We could have written it in a different way, but that's how we wrote it. So if we have a new node, then we need to add an edge from this node to one of the existing nodes. So a random number between 0 and I not included, which we can write in one line. And p, which is numpy, random rand int, and then low equals 0, high equals I. Right? That's how it works. Let's check. Yeah, right. We don't have to specify. It appears that if we don't specify the size of it, it just gives you one value, which is what we need. So low equals 0, high equals the maximum number plus 1. So we will never actually hit high, which means that I will never be connected to I. The smallest, the highest number it will be connected to, it can be connected to, is I minus 1, which is what we want. All right, so we did that, and we do return G. Let's try that. Reach club network. Sure, let's make a small one, 5. G equals this thing, print G. Does it work? Yeah, seems to be working. Let's plot it. G plot. We mostly get little sticks. Okay, 5. Let's try 10. Aha, aha, look, how nice. We tend to have a central node, isn't it? Somewhat different. Let's try to do 100. Okay, look at that. Oh, interesting. One interesting thing about this network is that it doesn't have cycles. Look at that. Because we always add a node to the existing tree. We have a tree. There is no way to create a cycle in this network because we never add an edge between two existing nodes. The edge always leads from an existing node to a new node, which means that, what does it mean? We'll see, it's interesting. So this network is very different from the other network in more than one way. The distribution of degrees may be different, but also it's acyclical. Good, good. Let's look at the degrees distribution. So in order to look at the degrees distribution, let's modify this thingy as well, so that let's turn it into a function. Plot degrees distribution. Define degrees g. So we'll have a function that gets a graph and plots the degrees distribution. Let's also add here a little line that would that would create a new figure. PLT figure. I think that's it, right? PLT figure. I think that's it. And let's hide the printing functions. I mean, the printing commands that create these lines of numbers. Let's just go with a plot. All right, so let's now move it upstairs, like here. And it's not quite plot. Well, also, you know what? Because it's a function, let's put the comment where it belongs into the documentation string. Calculates and plots the degree distribution for a graph. Good. So now gplot, let's do no, not g, degrees. How did he call it? Degrees. Degrees g. Okay, I've changed my mind. I want it to be pretty. So actually in the degrees, let me get rid of this figure. And instead, let me do this thing. Subplot 1 to 1 gplot, subplot 1 to 2 degree distribution. Nope. Oh, of course, yes. It's like PLT, right? Matplotlib. I think that's how it works. Yep, not very pretty, but it's okay. PLT figure, fig size equals 12.3, 12.4. Good. And then I can just copy this little snippet of code here. All right. So I haven't actually put them on the same plot. Should I? Nah. Grr. Okay, let's put it on the same plot. So let's go to degrees and make it return something. Let's make it return the x and y values for our plot. Just y values is okay. Return the hist. Okay, so the histogram. And then here I will add hist like degrees 1 equals, it's kind of awkward that, yeah, it's fine. Degrees, sure, degrees random equals degrees g. Now here I can do plt plot degrees random. Okay. Right? plt labels, label, legend. plt legend label equals, if I remember how to do it correctly, labels are rich club, random network. Nope. Oh, yeah, you just do it like that. Okay, so plt legend adds a legend in the corner. The labels you just apparently provide as a list of strings, and they become labels, and they should go in the same order in which you plotted the stuff. Now, while I created the networks, I first created a random one and then this tree, but I first plotted the tree with this command, and then I added a random network one with this command. So I have to put legends in the same order. I have to add a string rich club first and then random network second. All right. So let's see, let's stare at these degrees of distributions. Did we guess it right? So we guessed correctly that 0 nodes will disappear. Yep. We guessed correctly that 1 degree of 1 will increase. That's true. And actually, like, well, can we tell that really high degrees are more popular now? Yes and no. Like, look, in the random network, we didn't have any nodes with a degree above 7. In this particular run, like there is a chance of getting a node with degrees of 7 in here because everything is random. It's just not particularly likely. But for this network, yeah, we got a degree of 9. But at the same time, it's not like we got a degree of 20, right? So maybe I overestimated a little bit just how high we will go in terms of the maximum degree in this network. So the effect is kind of there, but it's not that obvious. So because this growth for high degrees was not that obvious, the decrease for intermediate degrees was not obvious either. So the biggest difference, I guess, is for degrees of 0 and degrees of 1. Good to know. We can relate to this now, which is nice. All right, now, okay, I can delete that because that's the old version. We migrated it upstairs. I can delete that because it's a description of this other network that we have now implemented, and it's left in this other document anyways from our last class. So time to build the disease propagator. So at this point, it's almost like this notebook has become uncomfortably long. Well, it's not too uncomfortably long, but it's getting there. So at some point, once we're happy with our implementation of the graph, for example, we would want to exclude this description, to take it out and put it into a module, into a file with an extension py for Python, py, and then we would import it in the same way as we import other modules. But so for now, let's keep it here because we may have to modify it a little bit. But at some point, like once it's more than, I don't know, 4 or 5 screens and scrolling up and down becomes hard and problematic, that's when you know that you don't want to, at some point, you don't want to keep it all in one notebook. You really want to start taking parts that are stable now, that you are not changing every day. You want to start taking them out into a module that you can just import and concentrate on things with which you're still messing, where you're still messing around. Okay, so disease propagation. How does it work? Let's start with pseudocode. Oh, for my YouTube purposes, let me stop the lecture and then I will restart it immediately just so that I had a different file.